Microservices. Who's doing microservices? Raise your hand high. Come on. It's cold in here. I can't see. How many people have been told that they're going to do microservices? Just a couple. Yeah, the CIOs that get those magazines, and they have some great ideas. My name is Christian. I'm a chief architect at Red Hat. I work with our customers in North America to help them understand what DevOps, microservices, cloud, all this stuff means for their organization, how they implement it using open source technologies. I spend a lot of time working in the open source communities as well. Some projects that you may recognize. Anybody heard of Apache Camel? All right. ActiveMQ? Couple? All right. Recently, I've been working on a project called Istio. Has anybody heard of Istio? Raise your hand. No? Couple. All right. We'll talk about it. Right, and so I've written a couple books. One of them, Microservices for Java Developers, that came out a couple years ago. And even though it came out a couple years ago, it's surprisingly, in my opinion, still relevant. Technology moves fast, but this book was written to be a hands-on guide for Java developers to begin writing microservices. And in a couple weeks at Red Hat Summit, we will officially be launching this book called Introduction to Istio for Microservices Developers. And if you go to developers.redhat.com, you can get free e-copies of both of the books. Okay, so what are we talking about? You know, we've heard a lot about Agile. We've heard a lot about going fast and using the cloud and these types of things. And we do that to build business value, right? We want to continue to figure out ways to bring value to your customers, right? Through innovation. But what is innovation? Who in this room, just kind of curious, who in this room can foresee the future? Anybody? Nobody? Oh, a couple people. All right, let's talk after. Innovation is admitting you don't have all the answers. There's a lot of uncertainty about what will work, what will deliver value. And what's interesting about that is we hire, our leadership to drive the company direction, but the truth is, even they can't see the future. There's a lot of unknowns, and the best way to figure out what direction to go when there's a lot of unknowns is to ask questions and observe and see the feedback and see if we're going in the right direction. So we need to figure out the right questions to ask, and to do that, we need to ask a lot of questions. And this is not unlike the scientific field and the way that they observe and innovate or discover new scientific breakthroughs. They make hypotheses. They make assertions that they think could be possible, and then they test them. And then they observe those results. So they run experiments, and they evaluate the results from those experiments, and they learn from that, right? And then they do that again. They continue to do that until they discover breakthroughs. And we ideally, when we talk about agile and cloud and this kind of stuff, there's a whole lot more to the value stream at our large organizations than just what technology you use, what framework you use, right? If you think about being agile, and then you realize, well, we're all just about every company every year goes through a budget cycle, right? And you plan out what's going to be the strategy for the next year, and then you come up with nice PowerPoint slides and ROI and justification. You get a project approved, and then you go and your job is to implement it, right? Now, if it comes in on budget, on time, that's great. Will that actually deliver value? Do we actually know until we get it out there? And the answer is in the research that we've shown, and the whole reason for the DevOps movement and lean management and startup and that kind of stuff, is that we don't know. Actually, 66% of the time, Microsoft did a study, 66% of the time, the good ideas that we have, that we went forward with, had zero or negative impact against the outcomes we were expecting. So it's not until you actually put stuff out in front of customers do we get to understand whether or not we are delivering value. So maybe a different way of looking at how IT works. So we talked a lot about cultural change and process and this type of stuff. Changing the way we work with the business. So the business, instead of treating IT as order takers, they're treating us as co-creators in trying to figure out what the value is. Instead of treating requirements as requirements, we treat them as hypotheses. This says, as a whatever, I want to do this so that whatever, that's a pretty strong statement to say, so that this. What we should be thinking is, we think, that if we do this, we'll get this result, and we'll know if the signals we were testing came back the way we thought they were. Otherwise, we get rid of that and come up with a different hypothesis. So doing this approach to this iterative, agile, if you want to call it, approach, which has been around for centuries, is in our IT organizations not feasible unless we have the supporting infrastructure and tooling to do that. So here's where the technology comes into play. Cloud native, microservices, cloud DevOps, all this stuff. Really, cloud native is the platforms, the infrastructure, the culture, the automation in place to make it economical to work in small batches to test these hypotheses, right? So we want to as cheaply as we can, test out these hypotheses and go really quick. That's the part about going fast. We want to learn. We want to make sure we're going in the right direction. You don't just hit the accelerator and close your eyes, right? You want to know that you're going in the right direction. And some of the studies, scientific studies that have been done by folks like Puppet Labs and Gene Kim, this is from the 2014 State of the DevOps report. And they were able to show that strong IT performance, so having this economic engine, this technology engine in place to go fast and deliver code to production, because that's when you know, that's when you get the feedback. The teams that were able to do this multiple times a day were considered the high performers, and the folks who were able to deliver maybe once a quarter, like a big bank where I used to work, they were sort of the lower performers, and they were able to show correlation between profitability, business outcomes with high-performing teams. And a particularly interesting note from, this is the 2015 DevOps report, but I think the 14 was very similar in this number, was that the difference between the high-performing teams and the low-performing teams was 30x. It's quite a big number. 30 times, the high-performing teams were 30 times faster at being able to do deployments. And they were 200 times faster at being able to take code from commit and get it into production, right? So this is 2015 or so. Since then, we've had containers, we've had automation, we've been focusing on making our IT systems more efficient. And if you look at the 2017 report, actually, I look at the 2016 report, and you see that the number it was at 200 times more frequent deployments, and 2,500 times faster developer lead time. But then you look at 2017, that number, that gap shrank, came down. We've been getting better at deploying, getting automated developer pipelines in place. We've been talking about containers for a while now, and we see in our customers that this tremendously helps in these throughput efforts. But look at the other two. Look at the change failure rates. Those did not change. Those went the other way. So we're going faster, but we're introducing more failures, or inability to recover from the failures as quickly as the high-performing teams, where they don't take that trade-off, right? So with any of these new methodologies, new to your individual organizations and technologies, then we should expect there's going to be some challenges in adopting that and making that feasible. But how hard can it be? We're supposed to be going away from very complex systems, trying to simplify things. Don't use SOAP, we were told, use REST now, because that's simpler. How hard can it be? REST services, A talking to B. We're building our systems as distributed components, and they just have to talk to each other like this. How hard can it be? Nobody really has a system like this. A doesn't really just immediately talk to B. It looks probably more complicated. When A talks to B, it's going to have to talk over our computer networks, which are made up of different computers, network switches, routers, physical cabling. And at any point between that communication between A and B, you can have network slowdown, routers hardware crash, maybe systems actually, the request actually gets to the other side, but that other side, when it responds, that gets lost somehow. As we move to these distributed services style architectures, we're moving a lot of complexity, which we kind of abstracted away in our co-located monoliths. Possibilities of failure modes, partial failures, all these things can now happen in our distributed environment. And we're pushing a lot of this complexity into the space between our services. Now you take that and you put that into a cloud environment where we talk about cloud being elastic, ephemeral, cheap to procure. These foundational pieces are inherently unreliable. So we're already talking over unreliable networks. Now we're saying that the components that the services run on, that's going to be unreliable. So these new challenges that we have to face, or we end up going fast but in the wrong direction. Some of these challenges include at the application networking level, how they interact and how they talk with each other. Service discovery. How many people have heard of the need for load balancing and service discovery in cloud and services architectures? How many people have heard of that? Nobody? Keith? Thank you, Keith. All right. Service discovery, retries, timeouts, circuit breaking. That's a fairly popular pattern people have been talking about now for 5 or 6 years, maybe even longer, 10 years, on the release of Michael Nygaard's book. Back pressure, outlier detection, health checking, deployments, being able to do fine-grained routing, canary deployments, certain types of rolling upgrades, and so on. A/B testing. These are all pretty big challenges when we start to go toward a services architecture, unless we forget security. As we start to break things up into smaller pieces and increase the attack surface and security concern for our architecture, we cannot forget about security. So the big internet companies who were the first to build their systems on cloud infrastructure, they invested a massive amount of time and resources into solving these problems. Google built out frameworks, so did Amazon. Netflix in 2009, 2010, when they started moving their architecture over to AWS, they realized quickly that they need to build this capability as well. They were nice enough, at least, to open source their implementation. Who's heard of Netflix OSS? If you can raise your hand. If you're Java developers, maybe you've heard of it, just a couple. So Netflix OSS is an implementation of the concerns, some of these new challenges that we have to implement. Netflix Hystrix was an implementation of a circuit breaker. So there's a library that you actually brought into your application to provide circuit breaking functionality. And in a circuit breaker, what happens is when you start making calls to an external service, it could be a database or another API, if that service or the network is causing failures or delays, you don't want to keep bombarding it with more traffic. That'll cause it to potentially fall over and others to fall over. So you can get into this nasty cascading failures jumping isolation boundaries in an unpredictable way, which is kind of what you're trying to avoid doing when you build microservices. You want your architecture, your application architecture, to be able to take some faults in its component pieces, but the whole thing to continue on. Circuit breaker helps prevent a cascading failures. Edge routing, so as traffic is coming into the cluster, can we get very specific about where we're routing these requests? Is this a platinum level customer? Maybe we want to put them over here on this cluster. If there's a non-paying customer, maybe we want to try out some new things on them and see how they react. Service discovery, load balancing, these are all built. Each one of these are individual application libraries. Java libraries in this case. They standardize on Java. And those libraries would be pulled into the application and left to each developer team to pull them in correctly and implement them. And they were successful. They worked around a lot of these distributed systems challenges. So kind of in a graphic, what this looked like is you had your different applications, their application code, and they would implement those application networking concerns inside of their application. Now, there are some drawbacks to this. So Netflix is the romantic Netflix story, but as the rest of the community starts to mature in their adoption of microservices, we find kind of quickly that there are some drawbacks. And even Netflix found these out as well. As you start to bring other languages to your platform, like I said, Netflix OSS is all Java. So the assumption was if you're going to do microservices at Netflix, it had to be Java. But not everyone shares that same opinion. Some folks might want to write their services in Node.js, or Golang is becoming popular, or Python, or whatever. Forcing a certain application language to implement your services architecture is a non-starter. How do you actually patch and maintain the library? So you have multiple deployments, maybe multiple versions, but if you find a security vulnerability in one of them or a performance issue in one of them, do you force them all to all the applications to upgrade at that same time? There's other things like sharing libraries in general. You're taking on the responsibility of maintaining somebody else's code in your application. We talked earlier about changing the dynamics between teams and owning the service. Responsibility is a big part of the DevOps philosophy. So maybe you say, all right, we'll use Netflix OSS, and then when we do Spring Framework or Spring Boot or any of these, they're built on Netflix OSS, so that's okay. It's all good. But I'm using Vertex. Maybe I want to use Vertex, which is a reactive programming framework for building services. Vertex does circuit breaking, load balancing, service discovery, routing, these types of things differently from the way Hystrix does it. It's a non-blocking reactive architecture. But like I said, maybe you don't want to use Java. Maybe your front ends, you want to use Node.js, the front end APIs. But maybe you don't want to do that. Maybe you want to use Go. Maybe you want to use Python, and believe it or not, some people still use Perl. So trying to maintain these 30 different libraries across different frameworks, across different languages, and hoping that each one of the developers is skilled enough to know how to use them properly and maintain them as changes come, as bugs are found, and so on. That is a pretty monumental operational task. And like I said, even Netflix is facing this right now. What we might want to do, and what we've done in some of the other patterns, for example, how many people are using Kubernetes today? Either for development, for testing, POCing, okay, a handful. There are a handful of these patterns that are kind of already baked into Kubernetes. So for example, with Kubernetes, you don't have to have an explicit service registration mechanism. When Kubernetes or OpenShift brings up a service, it's automatically registered. OpenShift's the one that put it there. It knows where it is. It knows its IP address. It knows its ports, all that stuff. So when a client wants to use a set of services, they can just they can assign one virtual IP for that cluster and use DNS inside of OpenShift. Now, you may have heard outside, like in AWS, like Netflix, for example, is a big opponent to using DNS for service discovery, and rightfully so, because DNS has is slow, has a lot of caching issues, and in a highly dynamic environment, you're going to get pretty stale data pretty quickly. Inside of OpenShift, you can use DNS, and you get service discovery out of the box, because that IP address never changes. The cluster might change, but the virtual IP that clients talk to doesn't change. So we already see that if you're a Python app or a Java app or a Golang app or whatever, you can get service discovery built into the infrastructure for free without having any special libraries. So what if we could do that with the rest of these concerns? What if we can take service discovery, smart load balancing, circuit breaking, timeouts, retries, distributed tracing, metrics collection, all these things that we have to do otherwise in libraries, and pull them out into a single binary that any application can use. You don't have to have special libraries to do any. These are all horizontal, non-differentiating concerns. So what if we take them out of the application, out of the L7, and push them down a layer? I know if there's any networking folks in here, you're going to come at me, but it's not accurate. But it's get it out of L7, right? Get it out of the application rather. Let's implement the concerns out of process, out of the application, potentially in a proxy. And that is what we have when we look at these application, level 7 application proxies, like Envoy proxies. Anybody heard of Envoy? Couple? Envoy is a service proxy written in C++ that is intended to be incredibly fast and flexible for application-level networking, like circuit breaking, timeouts, retries, these types of things that would otherwise jam into our application. It is that proxy. So in this model, the application talks to the proxy first, and then the proxy directs the traffic out from there. And I had here that it is a L3, L4. So it does, at its core is a byte processing filter or proxy, but there are L7, level 7 filters built on top of that. So it understands HTTP 1 and 2 and gRPC. And I think there are filters for MongoDB, DynamoDB, and folks are writing additional ones for Kafka, and we're going to see this continue to grow. Envoy came out as an open source project about 1.5 years ago. Came out of Lyft, the ride-sharing company, and they built this specifically to solve the problem as I illustrated it so far today. The author of the library came from Twitter, and Twitter built their own application-level language-specific libraries too. If anybody's heard of Twitter Finagle, and they had a lot of operational problems with that, just as I described. Another thing I want to point out is that it is written in C++, which is not an accident, and it's not because he's a big C++ fanboy. It was because the experience that he had with running JVM-based proxies or these libraries in a scaled environment introduced too much non-determinism at scale. The garbage collection, it could just kick in at any time, especially at the higher ends of the percentiles of latency. So Envoy is a proxy. It implements more complex application-specific load balancing and zone-aware load balancing, circuit breaking, outlier detection, timeouts, retries, traffic shadowing. So once I'll show you in a sec, the infrastructure that we're talking about here, we're putting it in place specifically to solve some of those problems, and sometimes around doing deployments, right? So if we're going to go fast and deploy quickly, let's solve and make that a lower risk activity. So these are some of the features of Envoy. We talk about it as a proxy that is out of process, that lives with the application, and in a deployment pattern that deploys highly coupled components of an application together is called a sidecar. Has anybody heard of either this sidecar or the deployment pattern sidecar? Anybody heard of that? A couple? So in a services architecture, it kind of looks like this. The service proxy is deployed alongside each instance of your application. So if you're Java, Tomcat or something, each Tomcat JVM has a proxy co-deployed alongside it. Inside that deployment, so if you're using Kubernetes, or if you're not, you should, inside of Kubernetes, there's a native support for this type of deployment pattern, the sidecar pattern. And in that model, or outside of Kubernetes, I guess, where the service proxy is deployed next to the application talks to the proxy, and any application that wants to talk to, so if any of these services want to talk to this, it goes to the proxy first. It goes through the proxy first. And the proxy then If you've done aspect-oriented programming or interception-based programming, this is kind of what it's doing. If as requests are coming in and requests are going out, it's applying this additional functionality to it. At the KubeCon in North America in Austin last year, there was a lot of buzz about this style of architecture, this deployment model. It's been termed the service mesh, and there was just a lot of excitement. People were seeing the light that in containers, in cloud infrastructure, that the Netflix model or the original V1 model is not sustainable. A service mesh then is a decentralized application networking infrastructure between your services. So we talked earlier about the complexity that arises inside or between the services as you start to distribute things out. That provides resiliency aspects, so I've been kind of mentioning that. Security, observability, so the ability to collect metrics, telemetry, signals, logging, distributed tracing, this type of stuff, and routing control. And we'll look at each one of these. But the service mesh itself is these proxies co-located with your applications and a control plane. So the proxies and that deployment is called the data plane. This is where all the requests and traffic's actually flowing through. And then the control plane, which actually controls the configuration and management of those proxies. And this is not unlike a lot of cloud, this architecture is not unlike a lot of cloud infrastructure, from API management to Kubernetes itself, all kind of built on this similar model. So all traffic between our applications flows through these proxies. And the proxies make up this data plane. Istio is a relatively new project. It was announced May of 2017. And it was launched by engineers from Google, IBM, and Lyft. And since then, other companies have got on board. It's growing quite fast. Companies like us, like Red Hat, Tigera, Weaveworks, some of these other companies. Istio is the control plane for a mesh made of these proxies, these service proxies. So Istio is the control plane, is the bottom part here of the architecture that allows users to configure it and control it and manage it in a large cluster. The components, real quick, that make up the control plane, the pilot. The pilot is what exposes the API for users or operators of the cluster to interact with the rest of the mesh and configure it. The mixer, and come talk to me afterward. I'm going kind of quickly through these. I want to show a demo. The mixer is a component in the control plane that all the proxies report back their telemetry to the mixer. And the mixer allows you to build plugins to plug in the telemetry into any backend system that you want. Datadog, Prometheus, whatever. And the types of telemetry, number of requests, failed requests, rate of requests, which endpoints are getting hit, distributed tracing like open tracing or Zipkin type telemetry. But the mixer also has, it's able to see what's happening in the cluster, but it's also able to enforce certain policies about who's allowed to talk to whom, who's calling whom too fast. So we can have quota access control like policies implemented in the mixer. The last component is the Sto Off Component. And this component is in charge of issuing and managing certificates to the proxies so that the proxies can then transparently encrypt the traffic between the different nodes. So in this case, the application doesn't know anything about, it doesn't have to know anything about language-specific certificates and key stores and trust stores and all this stuff that is a pain in the ass to put together. And developers typically either write it off or they check don't verify on the certificate and these horrible, horrible things. But with Istio, all the traffic between the services is automatically encrypted with mutual TLS. So all the traffic's flowing through the proxies, interacting with the applications. The control plane enables these things like policy control, security out of the box, and configuration of the behavior of the proxies. So with this in place, with this infrastructure in place, we have a lot more understanding of what's happening, the traffic that's happening in between our services, which is crucial when you start building distributed applications. You also have control points at every application, and you can control things like routing of requests that come in, not just at the ingress, but deep within the cluster. That a request that comes in with a particular header needs to go to, let's say, version 2 of our app, not version 1. Now, if you start to think about that a little bit, that functionality can significantly lower the risk of doing a deployment into production. If you can roll out a deployment into production, but guarantee it doesn't take any traffic, well, by definition, you should be able to test it and prod at it, but it shouldn't affect any customers. But then when you decide that it's going to take traffic, you don't just go from on to, or off to on in a big bang release type thing. You say, maybe I'm going to shadow the traffic. Maybe I'm going to take a handful of live requests, make copies of them, and send them to my new deployment. I'm going to monitor it and see how it behaves. I'm not introducing any customer requests into the critical path. I'm just shadowing traffic. Or I could say I only want 1% of real traffic to make it to my new deployment. And again, we'll watch it and see how it impacts customers. And then you can slowly grow that aperture as you find that it's acceptable to be deployed. Much lower risk way of doing a deployment. So Istio implements or gives the opportunity for applications to consistently and uniformly implement resilience concerns, timeouts, retries, circuit breaking, deadlines, these types of things. Sophisticated load balancing, client-side load balancing between the applications. Fine-grained routing and traffic control. I'll probably show you, if you're taking pictures, that's all good. I'm going to post all these slides online, so you'll be able to have all of them. Traffic shadowing, like I mentioned, where we can make copies of the traffic off to other deployments. Secure mutual TLS between the services by default. And observability, being able to get telemetry metrics about what's happening, what are the requests that are coming through the system and how frequently they're coming and how big they are and when are they failing and so on. Distributed tracing, so you can trace exactly where a request took its path in the cluster. Logging, these types of things. I'm going to quickly try to show a demo. If you want a deeper understanding or appreciation of exactly what's going on in an Istio service mesh deployment, if you go to this workshop, this will step you through each individual step. There is another workshop here that walks you through all of the different functionality of Istio, put together by the Red Hat developers team. The demo I'm going to show you resembles this architecture: a customer service, which talks to a preference service, which then talks to a recommendation service, and we're going to do some interesting things in between where preference talks to recommendation. So real quick, super quick, there's the slides. I'll put the slides here. Reach out to me if you have any other questions on Twitter or email. All that stuff's up there. And I do encourage you to reach out. I've had people ask, is it okay, really, to reach out? Yeah, it is. And then let me quickly get to a live demo. All right, now I know you guys are going to come up and ask me afterwards, so I'm going to just tell you. I'm not actually typing this, but it is a live demo. It's a script that types it for me, but it's a live demo. So we can see here we're running everything inside of OpenShift. We got our customer service, preference service. Preference talks to recommendation. And right now there's only one deployment and a V1 of recommendation. On the bottom pane, what we're going to see is traffic coming into the service. The traffic is going to customer, and then from there, the chain of service calls happens. So we can see that it's taking load. We're hitting V1 of recommendation. Everything looks good. So let's say we want to deploy version 2 of recommendation. Okay, so we're going to take a look at the deployment. This is a Kubernetes YAML. Oop. Can I do that? Nope. Damn. So this is a plain Jane Kubernetes OpenShift resource file that specifies what the application is, what the container, the Docker image is right here, example dash recommendation v2, and nothing special about that. What we're going to do is when we do the deployment is inject that sidecar service proxy so that when Kubernetes deploys this application, both the application and the proxy get deployed atomically. They get deployed together. So we're gonna do that. We're gonna call istio kube inject, and I know that went kind of fast. Don't know why it's doing that. And we come up here and we see that it added a handful of new things. It added the sidecar proxy as a container. Okay, so here's the original application up here. Here's the command line that we ran. Istio control kube inject, and we gave it the deployment descriptor. Now, that's one way to do it. You can also have Istio automatically inject the sidecar proxies when you do a deployment. You don't have to do it manually like this, but I'm doing this to illustrate how it works. So we didn't deploy anything. I just showed you that we can inject the sidecar proxy. Let's actually create it. Let's actually deploy it. We'll do a kube create or apply, and we should see it start to come up. We see down here that 1 of 2 was ready, and now 2 of 2 was ready. And down here, you should start to see that by default, the default behavior in OpenShift and Kubernetes is to, now there's 2 of them, so load balance across both of them. But that's not what we want. We don't want people to see version 2. We want to get it into production. And so this is a technique practiced by a lot of like Amazon and Facebook. Things are in production well before you ever see it, but some people might actually see it. They do A/B tests. They do very controlled release processes. This is not what we want to do. We don't want to make version 2 visible to anyone. What we're going to do now is using Istio, we're going to create a route rule that forces all the traffic to v1. Don't mind the 503s. We're going to come back to that. But now all the traffic will be going to v1. That route rule looks like this. So it's a YAML file, just like all the other resources in Kubernetes, but Istio is using a YAML file. Anytime we talk to the recommendation service, we're going to route 100% of the traffic to v1. Pretty straightforward. Now, the next thing we want to do is we do want to route some traffic to v2. So let's do that, and I'll show you this route rule in a second. We're going to route some traffic to v2, and you're going to notice that, well, it is, and it kind of looks like it's load balancing again. And that is true, because in this route rule, what we said was send 50% of the traffic to v1 and 50% to v2. Now, you probably, if you want to lower the aperture of the request's impact, you might just do 1%. Not 50, but I'm doing 50 here to show that we can split the traffic, and also there's a later part of the demo that having the traffic go to both equally will make the functionality more apparent. Next thing we're going to do is we're going to inject failures into our system. We're going to purposely cause 503s. Now, this is an aspect called chaos testing that forces issues into the infrastructure and tests whether or not the applications really are resilient, whether they really are built to withstand certain types of failures. In this case, since we have service proxies at each one of the applications, we have that control. We can just say, all right, for half the traffic or whatever the number is, we're going to, let's see, what did we set it for? 50% of the traffic, we're gonna halt the traffic with 503s, HTTP 503s. But let's say that we were actually experiencing network issues. We were actually experiencing application issues. With Istio, we can do something pretty simple. We can just add a retry policy that says if you see an error, then retry. These are transient, maybe these are transient network errors. Let's just retry. And as soon as that configuration propagates through, we should see the traffic start to, cross your fingers, I told you this live demo, we should start to see the traffic smooth out a little bit. So let's clean that one up real quick. Now we're going to look at a scenario which is even more dreadful than just transient network errors. We're going to look at when things start to go slow. Latency. Latency kills. So in this case, we're going to deploy a new version 2 of our application, our recommendation application. But this one is going to introduce 3 seconds of delay. So if we watch this, wait for this to come up, looks like it's come up. At the bottom, you should see the traffic going, but periodically it'll stop because it's hit that service that has a 3-second delay, right? And this is something our customer would see because we're calling this through the customer service. But we don't want that. But what can we do? We can introduce timeouts. We can introduce timeouts to force threads to give up their thread of execution when things are unexpectedly slow. Okay? So if we create a new route rule, and what we should see is when it hits, that we'll wait for at most one, we set the timeout for 1 second. If it hits that slow service, then just timeout, kill that thread of execution and just keep going. So now we don't have the latency and unpredictability of how long a request will take, but we're still getting these 504s. These are being throttled or killed. And so we don't really want that either. Let's look at the circuit breaking functionality. So again, I haven't touched any application code. This is all driven through Istio configurations. The next thing we're going to do is we're going to create, the last demo we're going to do is create a circuit breaking configuration. We're going to say that if there's, in this case the numbers are artificially pretty low, we're going to say if we have one error, then sleep. Kick that endpoint out. We don't want to call that endpoint anymore. Kick it out of the load balancing pool. So when we do that, let's create that. At the bottom, what we should see is the error that we're going to get is the 504. We're hitting the timeout. The 504 will kick up an error. The circuit breaker will see that and say, okay, we're not calling that endpoint anymore for 5 seconds, and back off from there. So we should start to see this kind of smooth out. We should see every once in a while, after that window has elapsed, that endpoint will come back into the load balancing pool, and we should see errors periodically. But we can also see that it's smoothed out the traffic quite a bit. The last thing we're going to do is we don't want those errors. We don't want those 503s. What's a simple thing that we can do when we get those 503s to get rid of that and smooth out the traffic completely? Retry. So we'll add the retry. And then once the configuration propagates, we shouldn't see any more 503s, any more 504s. We should just see nice, smooth traffic. And we didn't touch any application code. Doesn't matter if this is Node.js, Java, whatever. It's just a service mesh. All right, well, how am I on time? Where's Mike? 5 minutes? Or done? You will give me 5 minutes. I don't want to take Keith's time. Anybody have any questions? Good. I made it all very clear.
Wow, that was very clear. Oh, we do have one question.
Are the Istio control plane components redundant, or are they single points of failure?
Are they redundant, or are they single points of failure? Is that what you said? All of the components in Istio are both highly available, and if that component does somehow go down, the system is built to keep going. The system is built to keep going on the information, so it heavily caches configuration and that kind of stuff. So a control plane component, the mixer, the pilot, the CA, will not impede customer requests.
Any other questions out there? I was just curious, actually, in terms of the deployment, if you do the sidecars with the actual microservice, are those, from a container perspective, what patterns do you see around in terms of, do you combine those together with the container, or do they deploy a sidecar container with the microservice container? How's that been?
Ideally, you would want to keep them separate. So you wouldn't put the proxy inside the same container as the application. You want to keep them separate so that you can compose them at runtime. Yeah, that's a proper. And if you're not using containers, then you would have a proxy per host, typically.
Right.
Sorry? The overhead of the in terms of memory or latency or everything. So what I've looked into. So first of all, there is some overhead, right? But I looked at the overhead compared to what it would look like if you did Envoy next to an application versus your application, your Java application with 30 different Netflix OSS libraries jammed into it. The overhead, first of all, in terms of space, the Netflix deployment was like 2 or 3 times as big. The memory overhead, obviously, in Java is going to be significantly more. So there absolutely is overhead, but I think for the functionality that you're getting, the alternative, I don't see how you would do that. How you would do that without incurring similar, if not worse, overhead. Yes, and so Google does have, so Google from, I think it was 2010, 2011, they moved from an architecture where they had more centralized proxies where everything was going through into the distributed, the small C++ sidecar proxies that get deployed with their services, every container, and sometimes more than one sidecar.
One more question.
No, I was going to add to that. I think one way to think of this as well is if you have a cluster and you're running Kubernetes to manage the clusters, and then you have Istio that gives you this very fine-grained container-to-container, microservice-to-microservice control. And then often we also see customers who have things that are not on containers. You may have then Nginx proxies or other things like API management proxies, more standard, and all those can roll up to the same. So the Red Hat sort of way of looking at this is the API management layer can tap into Istio as well.
Absolutely.
So you're going to have a multi-layer onion approach to this, and you may have, some policies on the edge of this and some policies in the middle. They might be different.
Absolutely. Yeah. And then to that point, and even to the point that Maureen made earlier today, when she started talking about the sprawl of building applications and APIs across different cloud environments, maybe Azure, Google, AWS, on-prem, whatever. Istio is in its charter is intending to solve that communication federation problem across the clouds, to build a single domain, regardless of what the deployment architecture or topology is, to have the same level of access control, throttling, routing, this type of stuff. So right now it works on, and anybody going to Red Hat Summit? The Red Hat folks?
The Red Hat guys are.
So at Red Hat Summit, I'll demo this federation capability with a cluster running on Google GKE and on-prem OpenShift and potentially even VMs, bare VMs, and federating the services running across all of those different environments. So come to Red Hat Summit and get a copy of my book too. Any other questions? All right, well, thank you guys. Thank you all for coming.